Good day. I will discuss to you the last part of vector operations, which is known as scalar triple product. So we have here the definition of scalar triple product. It says here if vector u equals u1, u2, u3 as its components, vector v equals v1, v2, v3 as the component of your vector v, and w equals w1, w2, w3 as the components of vector w. So these are vectors in three space. Then the number u dot quantity v cross w is called the triple product of vectors u, v, and w. It is not necessary to compute the dot product and cross product to evaluate a scalar triple product. The value can be obtained directly from the formula u dot quantity v plus w is equal to, we have here a matrix, that is we have u1, u2, u3 as its first row. Then the second row is v1, v2, v3. And the last row is we have here the components of vector w equals w1, w2, and w3. So we have here a 3 by 3 matrix, and calculating the determinant will give you the scalar triple product. For the geometric interpretation of scalar triple product, we have here the following theorem. Let vectors u, v, and w be non-zero vector in free space. For the first geometric interpretation, we have here the volume V of the parallelepiped that has vector u, v, and w as adjacent edges is denoted as volume V equals the absolute value of the scalar triple product denoted by u dot quantity v cross w. Then for the geometric interpretation of scalar triple product, if we have u dot quantity v cross w equals 0, if and only if u, v, and w lie in the same plane. So it means that we have the scalar triple product equals 0. The three vectors are lying in the same plane and they are said to be coplanar. So in this figure, we have here the geometric interpretation of the scalar triple product, which is the volume of the parallelepiped. As we can see here, we have the formula of volume of parallelepiped is equal to area of base times height, and the area of the base can be defined rather by the magnitude of u cross v. Then the height is the magnitude of w times, we have here the absolute value of cosine theta. So with that, we now have the volume now is equal to the absolute value of the scalar triple product denoted by u cross v dot w. So the geometric significance of the scalar triple product can be seen by considering the parallelepiped determined by the vectors A, then we have vector B and vector C. So since we have known a while ago that the area of the base of parallelogram is equal to the magnitude of B cross C, so and its height can now be found by, we have the cross product of the two vectors B cross C. And that we now have, if angle theta is the angle between A and B cross C, then the height h of the parallelepiped is equal to magnitude of A times the absolute value of cosine theta. We must use absolute value of cosine theta instead of cosine theta in case the angle theta is greater than pi over 2. Hence, we have here now the formula of the volume of the parallelepiped is equal to volume is equal to, denoted as V equals area times height, where we have the area is B cross C, Then the height is denoted as, by the way, this is magnitude of B cross C times the magnitude of A cosine theta for the height. Or we can also simply state it as the absolute value of the scalar triple product of A dot quantity B cross C. So the volume of the parallel pipette determined by the vectors A, B, and C is the absolute value of their scalar triple product. Another geometric interpretation of the scalar triple product is the volume of the pyramid. And we can find the volume of the pyramid by taking 1/6 of the volume of the parallelepiped. So we have volume of pyramid is equal to 1/6 of the volume of the parallelepiped. And with that, we now have volume of the pyramid is equal to 1/6 of the absolute value of the scalar triple product A dot quantity B cross C. Or we can also have 1/6 times the absolute value of U dot V cross W if we have U, V, W as the given vectors, or we can also have B, C as the given vectors, so we can also use this formula. Let us have the following examples to apply the scalar triple product. So we have here, find the volume of the parallelepiped that has U, V, and W as the adjacent sides. So we have here vector U equals 2, negative 8, 2, vector V equals 0, 4, negative 2, and W equals 1, 2, negative 4. So in defining now the volume of the parallelepiped, we perform the scalar triple product. So we have U dot quantity V cross W is equal to, we have the determinant now, or others are a matrix, a 3 by 3 matrix, then we will define the determinant later on. So let's have the first row 2, negative 8, 2. Then you have the second row will be the components of your V, which is 0, which are 0, 4, negative 2. Then we have for vector W, we have it as 1, 2, negative 4. So we can apply basket method. So we having by having to copy the first two rows, we have 2, 0, or two columns rather, 2, 0, 1, then negative 8, 4, 2. So with that, we now have U that quantity V cross W is equal to, let's get now the determinant using basket method. So we have 4 times 4 is negative 16 times, so that's negative 32. Then we have plus, this is 16. Then we have here plus 0. Then minus, we have this as 8. Then this is negative 8. Then you have this as 0. So with that, we now have U that V cross W equals negative 32 plus 16 is negative 16. Then minus 8 minus 8 is 0. So the answer is negative 16. And for the volume of the parallelepiped, we have known that this is absolute value of U that V cross W is equal to absolute value of negative 16 equals 16 in cubic units. So this is how we compute the volume of the parallelepiped that has three adjacent sides, which are vectors u, v, and w.